Okay, here we go. So as I mentioned, next Friday is the goal in terms of when we will have our second exam. I want to sort of reiterate that I will ask some questions about power series, but the clear emphasis for that exam will be, understanding series, knowing which tests to apply in which situations, even recognizing indeterminate forms for limits of sequences, computing limits, and there will be a true-false section, no question, but the test typically ends up being a little bit shorter, and it's, but there's it's shorter, but it's more like because you're just making a decision in terms of converging or diverging, and you're identifying which test you're using. I will even have a section where you will have some series that you will have to determine the convergence or divergence of, and you will have to choose from among a battery of tests, and you'll only be able to use one of the tests exactly one time in the section. Does that make sense? So it'll be like 5 series and 5 tests, and what you'll have to do is match the test that you're using with the series you're applying it to, and that's how it will work. Does that make sense? Because sometimes there's more than one way to actually tell whether a series converges or diverges, but in this particular section, there is like the matching it one-to-one like that, you're going to have to choose carefully. Does that make sense? So I will have a section like that as well. So please do, if I were you, I would make sure to at least look through some of the problems, even up to the stuff on Taylor polynomials for sure, okay? I will definitely be testing more rigorously your knowledge of the last 3 sections of Chapter 9 later on, but I really want to make sure you have the series stuff down, okay? Any questions on that before we turn to our exploration of power series once more? Yes, Daniel. Well, no, not as much. I might ask you something about Taylor polynomials, but I probably won't be asking anything in any kind of depth as it pertains to power series proper. We're just now getting into that now. We'll talk about it more at the beginning of next week, and we'll actually finish Chapter 9 completely probably by Tuesday. But I won't be asking any high-level questions. I just want to make sure that you really can do the series stuff well. If you can do the series stuff well, I have no doubt you can do the power series stuff at least decently well. Okay? Other questions? And again, this is the we've ascended to the climax of difficulty, I would say, for even all of calculus, even including Calc 3. Chapter 9 is kind of the peak of difficulty, I would say. Okay? There's just some abstraction there. Some of the stuff just feels weird at times. Sometimes it's hard to even say what you mean in a correct way. And it's just tricky in that way. When we get into Chapter 10, it's going to start to feel more like you're in high school a little bit. So like we'll talk about conic sections. That'll involve things like ellipses, hyperbolas, circles, those sorts of things, okay? The stuff with parametric equations is going to be a little bit different, but I think you'll feel pretty good about it, okay? Other questions before we jump in here? Well, let's keep going. Here we go. Again, this should not be a shock from what we were talking about with Taylor and Maclaurin polynomials. The only difference is we just don't ever stop, yeah? We just keep going. And we build a so-called power series in the same way. And even the formula itself is the same, right? For the coefficients, this formula that's sitting right here, right? That formula is exactly the same as it was for the polynomials itself. That's not surprising. You would still proceed by taking derivatives and then solving for those coefficients in the same way, so you should get the same formula. Okay? And again, in the case where we have powers of x minus c, the best approximations happen at c. The further away you get from c, the worse the approximation gets. Yeah. In theory, it could get worse, but of course, it's a power series, in which case, you know, maybe the approximation is still perfect out to a certain point, and that's part of the discussion that we're going to have. Okay. What we're going to be doing today is exploring these questions. We brought them up at the end of last time, but the question is, somebody hands me a power series, and I need to know which x values I'm allowed to plug in. You know what I mean? Can I plug in x equal to 50 and have the power series converge? Can I plug in x equal to 7? Can I plug in x equal to -3? I want to know which x values I can plug in. And so that's going to be what we're going to be exploring in depth today. Typically speaking, a couple of tests that will help us to this end. So for what x values does a given power series converge? The two tests you use the most often to that end are the root and the ratio test. Okay, the root and the ratio test are the big two. Okay. Now remember, the root and the ratio test told us stuff about absolute convergence, yes? And it said if one thing happened, namely if the limit of either the ratio of the terms or the nth root of the terms goes to something less than 1, you have absolute convergence. And if those limits end up being something greater than 1, then you know the series diverges. And if the limit is equal to 1, what's the conclusion in each case? That you can't make a conclusion, right? It's inconclusive. So what you'll have to do is the places where the limit is equal to 1, you'll kind of have to do a special analysis on its own. And we'll talk about that a little bit more. Every power series converges at C. We talked about that, right? If I plug in C, so f of C, of course, you know, if I were to write this out, this is like A0 plus A1 times x minus C to the first, plus A2 times x minus C to the second, plus et cetera, et cetera, et cetera. If I plug in x equal to C, everything dies from the second summand onward, yes? The only thing that survives is the constant term, right? So clearly this series converges at least at C, at least at the center itself, okay? And the question is, okay, are there other x values I can actually plug in, okay? And so last time I pointed out that there are 3 situations. One is that all you have is convergence at a single point, namely at the center. The second is that you actually have an interval, a symmetric interval about the center where you have convergence. And this number r right here, does anybody know what that's called from past experience, r? It's called the radius of convergence. Basically, you can take any x value in this, interval, and you will be able to, you will know beyond any shadow of doubt that you have convergence, okay? The reason it's called the radius of convergence is because you can go either direction from C by R units and still have convergence, okay? That's why it's called the radius of convergence, right? After all, you know, that's what this would be if you actually drew in a circle right here. Does that make sense? With like C at the center, then this would be the radius of that circle. Does that make sense? Okay. Or if you're really fortunate, you might find yourself in the situation where you can actually plug in any x value at all. In that case, you would actually say that the radius of convergence, I mean, it's kind of silly, but, you know, Look, this thing just goes out forever. So the radius of convergence here would actually be plus infinity. Does that make sense? You would actually say the radius of convergence is infinity. And you can literally plug in any x value at all, and you would get a converging power series. Okay? So the three possibilities are that you either just have a single point of convergence, namely the center, an interval centered at C. Okay, so a single point, right? The single point situation is just x equal to C itself. An interval centered at C, well, that means that it's going to be like C minus the radius and C plus the radius. Okay, and by the way, you may be able to include the endpoints. You may be able to include one of the two endpoints. You may be able to include both of the endpoints. We will see situations like that. So this is often referred to as the interval of convergence. Okay, so it's like the interval of convergence. So we have the radius of convergence and we have the interval of convergence. And the interval of convergence, let me just say that this may include endpoints. Okay, you have to do a special analysis to sort out whether that happens. Or you have the entire real number line as your collection of numbers that you are allowed to plug in. That's the case where the radius of convergence is plus infinity, right? So those are the three options. There are three options here, okay? All right, any questions on that? We're gonna start looking at some examples here just to clarify what it is we're talking about. But any questions on that before we move on? All right. Moving on then. Let's do this. You ready? Oh, that last example down there is a little bit cut off, but maybe in the world, what's going on here? Oh, no, it's good. It's good. Okay. So let's do the first example and the second example. Okay. And then I'm going to turn you loose on some of these further examples. I want to determine the radius and interval of convergence for the following power series. And in each one of these cases, you basically want to think of this guy right here, the entire thing, the stuff and the power of x. You want to think of that as like an. Does that make sense? Think of that whole thing as an. And I'm going to do two paths in this particular case. I'm going to do the ratio test first, and I'm going to do the root test, just so we kind of see both of these in action for this first example. So in the ratio test, first of all, you always look at the absolute value of the next term over the current term, yes? So you look at the absolute value of an plus 1 over an. Okay, so the absolute value of an plus 1 over an. Okay, what's that going to be? So what is an plus 1 going to be here? Think about it. If an is like all that junk, what's an plus 1 going to be? 2x to the n plus 1, basically, yeah? Right? And David's sort of saying, hey, you can peel off an extra factor of x in that case. But yeah, it's going to be absolute value of 2x to the n plus 1 over the absolute value of 2x to the n, yes? And hey, what's kind of interesting here is there's a lot of cancellation that happens. For instance, what about the 2's? Those clearly cancel. Okay, what about x to the n? Yeah, those are like almost all the x's cancel except for 1. Does that make sense? Okay, so like, right, all of these cancel, and we are left with simply a single factor of x in absolute values. Do you know what I mean? So that's going to be just absolute value of x. And then we take the limit as what? We take the limit as n goes to infinity. And look, there's not even any n's in here. Do you know what I mean? So where's this going to go? Excuse me, it just goes to the absolute value of x. And to get convergence, what had better be true about this limit? What had better be true about this limit? So to converge, limit needs to be what? Needs to be less than 1. So I impose that on the limit. The limit is absolute value of x. That limit needs to be smaller than 1. And now you see which x values you can actually plug in. Absolute value of x less than 1. Well, what does that mean? What does absolute value of x less than 1 mean? That means that -1 is less than x is less than 1. What is the radius of convergence, by the way? 1 is the radius of convergence. Do you see what I'm saying? What is the center? Okay, I'm just trying to write everything down. The center here is 0. We kind of knew that from the beginning because it was just powers of x. The radius of convergence is 1. Yeah? Okay. So look, I will have convergence if I plug in any number between -1 and 1. Now, a question that you should ask yourself, though, is what about the endpoints? What about the endpoints? Okay, so let's kind of look at that quickly. So endpoints. Okay, what about the endpoints? What are the endpoints? X equal to what? So x is between -1 and 1. I have convergence. What are the endpoints of the interval? Not a trick question. -1 and 1. And the question is, can I plug in -1 or 1 and get a converging series here? If I plug in x equal to -1, look at how stupid this is. So that is, I'm plugging x equal to -1 into this series. If I plug in x equal to -1, what series do I get? Look how stupid this is. It's going to be sum n equals 0 to infinity of what? 2 times -1 to the n. Do the terms even go to 0? No, in fact, the terms are going to flop back and forth between -2 and 2. You know what I mean? So this series diverges by what? By what test am I technically using? Yeah, so by nth term test. And by the way, x equal to 1 is like even worse. Do you know what I mean? At x equal to 1, it's just the sum of 2 an infinite number of times. Do you know what I mean? So at x equal to 1, the series diverges also. Okay. Therefore, I have my radius of convergence. It's sitting right here. Here is the radius of convergence. It's 1. Okay. What about the interval of convergence? Interval of convergence. Okay. A lot of times you write capital I. In this case, I is just -1 to 1 without including the endpoints. Yes? The interval of convergence could include the endpoints if indeed we had a converging series there. Okay? So you kind of see how that works? We applied the ratio test. We discerned, okay, what's my radius of convergence? Which is basically half the length of the interval. Yeah? Okay? And then I said, okay, here is an interval where I have convergence. Can I include the endpoints or not? We said no. Therefore, the interval of convergence is just what we would call the open interval from -1 to 1, where I do not include the endpoints. Okay, what about the root test? Let's take a look at this guy right here. I'm going to move this thing down just so that we have a little bit more room. Okay. If I wanted to do the root test, what I would be doing instead is I would be taking the nth root of the absolute value of an. But of course, that means I'm taking the nth root of the absolute value of an. That means, you know, the absolute value of 2x to the n. And what's going to happen to the x to the n and the nth root? What happens there? It's just x, but again, it's an absolute value. Do you know what I'm saying? Like I can pull the absolute value inside. So let's see here. This is going to be 2 to the 1 over n times the absolute value of x. And what happens to this as n goes to infinity? What happens to 2 to the 1 over n as n goes to infinity? That goes to 1, and I'm just left with the absolute value of x. And I would go through the same rigmarole we just did, right? I would say, here's the limit. What do I need to be true about the limit in order to get absolute convergence? The answer is I would need this limit to be less than 1. And on and on and on this would go. Does that make sense? You would do the exact same thing at this point that you did when you applied the ratio test. Okay, please ask questions about that, okay? Apply the ratio test or the root test. That will tell you, you know, you take the limit. That limit needs to be smaller than 1 to guarantee convergence. Yeah? And then you build your interval from there. You can find the center, the radius, you check the endpoints. That will tell you what your interval of convergence is, yeah? And that's basically the game that we'd play, okay? All right, please ask questions. Any questions on that? Yeah. Well, no. If the limit of the ratio goes to 1, you don't know what's happening. It could converge, but it could diverge. That's why we have to check. That's why we have to check the endpoints. You could have convergence, potentially. In this case, we didn't, though, right? Right, we ended up having divergence at the endpoints. Okay? Does that make sense? Does the strategy kind of make sense, how we go about doing this? Okay? So let me kind of, let me clear this. I'll actually write our conclusions up here. So the radius of convergence for this guy was 1. What was the interval of convergence? It was -1 to 1. So that means I'm allowed to plug in anything strictly between -1 and 1, and I will have a converging series. Okay? All right, what do you guys want to try on this next one? What do you think we should try on the next one? Remember, the first thing we do is we kind of set an equal to this junk right here, yeah? Okay. Which test do you think is going to be more in line with, you know, with getting what we want? Yeah. The root test? Okay, well, the problem with the root test is I don't know what the nth root of n factorial is. We could, Daniel, we could use the root test, but what would we have to invoke? We would have to replace n factorial with a bunch of junk. You have to invoke Stirling's approximation. That would work. The ratio test will work nicely because a bunch of junk will cancel. You know what I mean? Okay. All right, so let's use the ratio test. Okay, so that means I want to go the absolute value of an plus 1 over an. Okay, what do I have here? An plus 1. What is an plus 1? What's going on? What's going on here? Yeah, okay, so you're already kind of thinking ahead here. N plus 1 times n factorial. It's basically n plus 1 factorial. And what about the x? X to the n plus 1. Maybe I should write that as just, what do you think? Yeah, x to the n times x, right? That's x to the n plus 1. And I'm dividing this by n factorial x to the n. And all of this is an absolute value, yeah? What cancels? N factorial and x to the n. Those both cancel. And all we're left with That's interesting. Watch this. Okay, all we're left with here is the absolute value of n plus 1 times x. Okay, and what am I going to take? Oh, and by the way, I mean, this is sort of stupid, but like, I don't really need the absolute value around, the only place I need the absolute value is around x. What happens is if I take the limit as n goes to infinity of this thing? Well, a couple of options. If x is anything other than 0, what's this going to go to? Infinity. This is like plus infinity if x is different from 0. Yeah? But what's it equal to if x is 0? Yeah, it's actually 0 if x equals 0. So is it ever possible to make this limit less than 1 if x is different from 0? No. Okay, of course, in this case right here, 0 is obviously less than 1, right? So what do we conclude in this case? What's the conclusion? We only have convergence at one point. Where is the convergence happen? I mean, there's only one point that actually gives us, if I move away from 0 at all, I get a limit of the ratio of the terms that is going to infinity, which it's impossible for me to make that less than 1, right? So what's the conclusion? We only have what? Only have convergence at x equal to 0. There you say the radius of convergence is 0. Do you know what I'm saying? There's no room around the center at all. We only have convergence at the center in this particular case. Okay? So let me actually, hang on a second. So any questions on that? Because this was a less than symbol, by the way, just to be clear, that's less than 1. 0 is less than 1. So I obviously have convergence if x is 0, but not if x is different from 0. Yes, Maria. No, because if this was actually 0, Maria, what would this be equal to before I even took the limit at all? That would just be 0 all the time. Does that make sense? So you'd be taking the limit of a kind of a stupid sequence. It would just be 0 all the time. Does that make sense? So I haven't let n go to infinity yet. It's 0 before it even starts to go there. You're at 0. The indeterminate form is problematic when you're like getting close to 0, right? And the other thing is getting close to infinity. And the question is, what's happening? Okay, that's a good question. All right, so other questions? By the way, that's not that surprising. I mean, that slapping an n factorial in there is like, as your kind of constant term is problematic. N factorial is massive, you know what I mean? So, all right. So let's see. What is the, so let's, just to rehash, the radius of convergence in the first case was 1, and the interval of convergence was -1 to 1, without including the endpoints, okay? And what was the radius of convergence for this second series? This is kind of silly. The radius of convergence is 0, and the only place we had convergence at all was at c equal to 0, yeah? Okay, so what I want you to do is to look at this next example with someone right around you and determine what the interval of convergence is for that thing. Determine what the radius and the interval of convergence is for that third one right there. Okay, so work on that for several minutes. Okay. All right, let's talk about this. So What did you guys do? So if you think of this as being like AN, what did you find to be easier, ratio or root or what? Root? All right. Okay, so let's do the root test. Okay, which means what? Which means I need to take the nth root of the absolute value of AN. Okay, if I take the absolute value of AN, and then I take the nth root of that, what happens? Yeah, let me just kind of write this out right. So this is going to be the absolute value of x minus 3 raised to the n over n, yes? And if I take the nth root, then I just get absolute value of x minus 3 over n to the 1 over n, right? And this is where I remember I was kind of hounding you guys about that limit, how it comes up all over the place all the time. N to the 1 over n, what does that go to? 1. So the bottom goes to 1. So overall, this goes to x minus 3. And if I want convergence, this limit needs to be less than 1, right? So I do this to converge, right? To converge, I need that limit to be less than 1. Well, what do I do with that information? Absolute value of x minus 3 less than 1. What do I do with that information? Right, you kind of figure out where x has to live. Absolute value of the thing less than 1 means that the thing inside the absolute value is between where and where? That means negative 1 is less than x minus 3, right? Didn't you do this like in high school at some point, right? It's less than 1. Like absolute value of the thing is less than something. That means the something, or less than something, that means the thing inside the absolute value is between negative and positive of that thing, yeah? Okay? So what does that tell you? If I add 3 to everything, where does x live? 2 less than x less than 4. So where's the center? Where's the center? Think about it. What's the center of this interval? 3. But you kind of knew that already, didn't you? Because this was in the form x minus 3, yes? And what is the radius? How far out are we going away from 3? 1. Okay, the radius is 1. And then what's the only thing left to do? What do I have left to do at this point? Endpoints? Okay, because I don't know the interval of convergence yet. So the endpoints are at 2. Okay, so if I plug in x equal to 2, what happens? What series do I get? Think about it. If I plug in x equal to 2, what do I get? Series in going from 1 to infinity. I plug in 2. 2 minus 3 is negative 1 to the n over n. Hey, that's the alternating harmonic series. Know what I mean? And what's the deal with that? Yeah, that converges. Okay, the other endpoint is x equal to what? 4. And if I plug in x equal to 4, 4 minus 3 is 1 to the n, which is 1. And I just get sum of 1 over n, which of course we know does what? Diverges. Okay? So what is the interval of convergence? The interval of convergence is, like there was going to be a 2 was on the left and 4 was on the right, but up until I looked at the actual endpoints, I didn't know whether I was going to have convergence on one side or the other, but now I do. I'm allowed to plug in 2, but I am not allowed to plug in 4. Does that make sense? So the interval of convergence here is 2, and you include 2, but you exclude 4. Does that make sense? Hopefully. Okay, here's your center, here's your radius of convergence, here's your interval of convergence right here. Okay, this is how these problems work. By the way, you could have used the ratio test on this. Do you know what I'm saying? You would have to compute the limit of like n+1 over n or something like that, or the opposite of that. But that limit goes to 1. But the ratio test would have worked equally good on this. But the root test worked just fine as well. Questions on that? Any questions? You may be asking yourself, hey, this is like a power series, right? So for instance, this first thing right here, that's like a power series, right? But what is that? I mean, is there like a function that's equal to, like an ordinary function that's not like an infinite sum of powers of x? Is that equal to some kind of function? And a lot of that's a legitimate question. Sometimes eventually we're going to have intuition about, oh yeah, that's just the exponential, or that's just cosine, or that's just sine, or that's just logarithm of 1 plus x or something, right? We will actually have a list of known power series that represent some function that we know stuff about. In this case, I'm telling you, you actually know what this is. So the question is, what is this? What is this? Okay. Well, I'm telling you, look, this thing equals, can't I factor out the 2? I mean, for crying out loud, right? Yeah, I can factor out the 2. This is like 2 times, and then it's like x to the 0 plus x to the 1 plus x to the 2 plus x to the 3. Do you know what I'm saying? Okay. So this is 2 times 1 plus x squared plus etc. Don't we know a formula for that? What does that look like? Don't you remember, like AR to the M plus AR to the M plus 1 plus etc. What did that end up being? Over 1 minus R, and that was provided that R was an absolute value less than 1, yes? Doesn't that look like this down here? It looks like X is playing the role of the common ratio. It looks like A is 1, it looks like M is 0, yeah? So I can just use that formula here, and this is going to be 2 times, okay, what is 1 plus x squared plus etc.? What would that end up being? It's the first term over 1 minus the common ratio, yes? So it's 1 over what? 1 minus x, and that is only true if what? What has to be true about x? X has to be an absolute value less than 1. But that's true anyways because the interval of convergence was -1 to 1, not including the endpoints, yes? So what function is this? Well, it's just 2 over 1 minus x. It's just kind of a funny way of writing 2 over 1 minus x. You can write it this way as a power series. Does that make sense? Okay. That's something that we will actually recognize very quickly later on without having to like think super hard. We'll just be like, boom. Oh yeah, that's just 2 over 1 minus x. Okay. So by the end of this chapter, we'll be much more adept at recognizing those kinds of things. Any questions? Any questions? By the way, number 2, that guy's kind of a stupid power series anyways. It only converges at 1 point. The third one, I'm telling you, we actually know what that function is. It is a power series, right? But I'm telling you, it's represented by a particular function that we've already encountered. I mean, you may not realize that at this point, but I'm telling you, it actually is a particular series that you already encountered. Do you remember one where it was kind of like thing raised to the n with like perhaps an alternating sign, and it was thing raised to the n over n? Do you remember something like that? Didn't we have that before? What was it? Do you remember? Well, here, let me kind of jog your memory here a little bit, okay? I think it was this one right here. Didn't it look like this? Yeah? It had something to do with the logarithm function, okay? So eventually we will be able to easily recognize these kinds of things. I just wanted to point out that there really is kind of a way that you can look at something and say, oh yeah, I recognize that as some rendition of the logarithm function. We would be able to tweak that and actually get a logarithm function to pop out. Okay? All right? Any other questions? What in the world is going on here? Come on, good. Oh wow, now it's black. Okay. I think it's time to stop. All right? All right, have a good weekend.